All right, we are now on take 4. Hopefully I can get through this without any technical snafus. All right, so we're looking at free response 32 for Barron questions, and it has to do with linear regression. It's a really dense question here, and I hate to say dense. I won't even necessarily say it's a difficult question, but you can take it so many approaches to it that I wanted to take a moment to talk about it. You're looking at a simple random sample of apartment listings in a large northeastern city where you're seeing the monthly rent versus the square footage. And you get a computer output, you get a scatter plot, you get a residual plot. You have to answer some questions here. Now, first question is a linear model appropriate for this data, and explain why? Here are the approaches I would take. Now, you might have taken a slightly different approach. Maybe you had some more details. That's fine. This is the way I would approach it, though. First, I would take a look at this scatter plot. Now, if I look at this scatter plot, if you look at the data, it gives you a very clear linear pattern. You can easily detect the line of best fit here. Now, this is without even necessarily looking at the least squares regression equation they're giving me. I can look at this and say, wow, that looks really linear. I can easily draw a line of best fit, and it seems to fit. So that alone tells you that a linear model would be very appropriate because your data is really clustering around a very obvious line here. The second way I would approach this is I'd take a look at my residual plot. I'm going to draw a line, right at the 0, which means, remember, if it's 0 residuals, that's exactly what they were predicting. Now, when you're looking at a residual plot, you want to make sure that there's no clear pattern visible. Like if you saw something like this would not be good for a residual plot. You do not want to see that. Even though it appears linear, this isn't a scatter plot. This is a residual plot. It's telling you how far your predictions are off. So you really don't want to see a pattern. Like here's another thing you would definitely not want to see on a residual plot. You won't want to see something like this either. You want to see something that looks kind of scattered. And if you look what we have here, we do have our residuals. They are fairly scattered here. That's good. You want to see that in a residual plot. So the fact that I'm looking at this, I'm not seeing any real clear patterns. That leads me to believe I'm dealing with a pretty good linear model here. The other approach I would take is I would take a look at the R-squared value. This tells me the percentage of values that are accounted for within my data that are accounted for by my least squares regression line. 94%. If I take that R-squared value, which I did off to the side here, right here. I found the square root of it, which gives me my R value, and that tells me the strength of my line. Now, the strength, we're getting 0.973. Considering 1 is the strongest value possible, this is really darn close to 1. So I can also jump to the approach here that since I have such a strong R value, and I'm going to double check, yep, my slope is positive, so that's going to definitely be a positive R value. I can look here and say, well, since I have a really strong R value, 0.97, I have a scatter plot that gives me a very clear linear pattern, and my residuals don't have any clear patterns to them, I can say that a linear model is definitely appropriate for this data here. It says interpret the slope of the regression line next. So what I did was I wrote out the equation. I started with y equals a plus bx. I then used the computer output here to fill in my values. So I have my constant, and then I have my slope down here. So what I did was I just plugged those values in so I could get myself an equation. Now what you want to get used to is you don't want to just leave it like this. You always want to throw context in here, which is what I did below here. If you notice, my y-axis is the rent, and my x is the size. So I just plugged in my values here. So I did rent. I'm even going to put dollars in parentheses so I know it means in dollars. My constant, or my y-intercept, is negative 311.34. So that represents feet squared. So I included that too, actually. No, it doesn't. It's not feet squared. It is dollars. So I'm going to change that. Negative $311. I know, it seems kind of crazy, but we'll talk about what that means in context in a moment. And then for slope, I know a lot of times we're programmed for this whole rise over run, but it's really good to approach it from change in y over change in x. So since my y values are rent and my x is size, that's telling me that for every square foot, I am paying $1.08, basically. And that's starting at paying, when you're paying negative $311.34, you're going to pay an additional $1.08 per square foot that is added in. Now, of course, it doesn't really make, in reality, no one's going to be paying you $300 to live someplace. You're not going to have a negative rent. But this is just telling you based on this model. Starting at negative $311, you're going to pay an additional $1.08 for every square foot that you're going to be living in. So that's how I would interpret that slope of the regression line here. And then lastly, we have to interpret R squared in context. Now, R squared, that is the percent of values accounted for by your least squares regression line. So what I can say is that 94.7% of my data is accounted for by my least squares regression line. So ultimately, that's why I get this really strong linear pattern, because about 95% of my data is accounted for by that, which means it's accurately predicted by my least squares regression line. So ultimately, that's how I'd answer these questions. And I'm also going to use this as an example to talk about extrapolation a bit. We talked about extrapolation and how it's a bad thing. Now, extrapolation is when typically you go beyond the data that you're given. So what that might look like is, say I wanted to figure out, okay, the rent for an apartment that's 3,000 square feet. In this case, you're going to notice our data only goes up to 2,000. If I go up to 3,000, 3,000 square feet, an example of extrapolating would be plugging that in here. So let's see. Oh, I forgot my X. So an example of that would be like if I wanted to figure out the rent for a 3,000 square foot apartment, I'd be starting out with negative $311 plus an additional $1.08 for every square foot for 3,000. That would be extrapolating because I'm going way beyond my data here. That would be plugging that in and then trying to figure out my rent based on that. It might be accurate. We don't know, but that's the thing. With extrapolation, you're taking a big chance and you really don't want to do that. Likewise, maybe if I wanted to figure out, maybe I have $3,000 to spend for rent. Maybe I want to plug in 3,000 instead and then figure out, okay, how big of an apartment could I get for $3,000? So I do that. Okay, well, maybe I have $3,000 a month to spend. And then you figure, okay, well, maybe if I plug that in, I can figure out how big my apartment would be. Again, that's extrapolating. You might not find it to be terribly accurate. It can also go in the other direction. Heck, I'd even say extrapolating in this case would probably be going down to 800 feet. Like, say, the lowest is 1,000. If you go down to 800 feet, that would be an extrapolation because we're going beyond our data here. So you really don't want to do that because you're going to find that sometimes it's not going to be very accurate. The reason is you're dealing with a very specific range and you really don't know what happens beyond this range. So extrapolating would be going beyond the range of data that you have. So I just wanted to go over that because, again, this question's pretty rich and I just wanted to go over the different approaches you could take. So again, for a linear model, what I checked was my scatter plot, my residual plot, and my R value. For my slope, I just remembered that, okay, it's change in Y over change in X. My rent is my Y. My X is my size here. So then I just looked at my computer output, plugged in the value, and I was able to interpret that a bit. And then R squared, again, that's the percent of data that's accounted for by your least squares regression equation. Hopefully that helps you interpret this a little bit, and it helps to see how